The title of our session is C++ Today, the Beast is Back. My name is John Kalb, and this session is based loosely on a book that I wrote with Gaspar Asman of the same name. This was published by O'Reilly. O'Reilly paid us to write this book. Not very much, but they paid us to write this book, but they're giving it away free. If you go to this URL, you can download this free. Now, I'm not saying this to promote the book. Obviously, I'm getting no royalties. The reason I'm saying this is because the story of this book is something about what this talk is about today, and that is that O'Reilly paid us to write a book they're giving away free. Now, Tim O'Reilly is not an idiot. He understands he's not going to make that up in volume. What's their business model? Why would they pay us to write a book that they're giving away free? Well, part of the answer, of course, is right here. O'Reilly is trying to gauge interest in this topic and collect emails so that they can sell books that are a little bit more, it's a little unfair to call it a book. It's more of a booklet. Thank you very much. They call it a report. And so they publish reports on hot new emerging topics of technology with the idea that they're capturing interest, that they're going to sell videos, books, other content later. Notice I said new technologies. Now, C++ has only been in existence for about 30 years. Why is it a new technology? Well, it is a new technology, and that's what this talk is really about. But to get to why it's a new technology, we're going to go back a little bit in history, basically to the beginning of computing. Who can tell me what that is? The difference engine. Well, it is not actually the difference engine, but it is a model built to the specification of the difference engine. And who's peeking around from behind there? Charles Babbage, that's right. So the reason I have this photo here, other than just the fact that it's kind of gee whiz and pretty for people who are techno geeks like me, the reason is because I want to point out that very, very early computing devices, and I mean very early, they of course operate on data. They do, but the operations on the data were really part of the computer, right? It was what we consider the software was really part of the hardware. That was that's how it manipulated the data. The algorithms were baked into the machine. Anybody know who this is? Von Neumann, yes. He's the one who pointed out, he said, computers operate on data, but the instructions to operate on data are themselves data. And so a computer should be able to hold the data that operates on itself. And so any machine that runs software that's part of its own data is called a von Neumann machine. And basically at this point, all machines are von Neumann machines. Who recognizes this? Who can tell me what this is? So most people can tell me this is assembly language. At ACCU, they tell me it's 6502 assembly language. That tells you something about where we are. So this, of course, are the actual instruction codes, the numeric values of the instructions, and this, of course, is the mnemonics. And when we call it assembly language, it's kind of a misnomer. There is no single assembly language. Of course, every computer platform has a language that's a distinct language for it, but it maps to the exact instructions of the machine. In other words, anything that a machine can do, we can express in assembly language. And in fact, this would be the language then that computing professionals and people writing system software would, of course, want to write in assembly language. Why? Well, the reason is because system software, being at the base of the stack, has to be very fast, right? You can't write any code that's faster than the system software on which you're basing it. And at the same time, this is how you're going to be able to exploit whatever hardware is exploitable. Anything that can be done, there's nothing between you and the hardware if you're writing in assembly language. But suppose you're a scientist. What is it that you want as a scientist? Well, you want to harness the computing power to solve the problems that you want to solve. Calculations that are either very tedious or error-prone, that's exactly what the computer can do. But you're probably not interested in squeezing the very last percentage of performance out of your computer. You're, of course, interested in as much computing power as you can have. That's not the same thing. And, of course, you don't really care about the details of the machine. You want to be hidden from that. So you'd really, really like to express your problems in some way that is not tied to specific hardware, that is portable. And so John Backus gives us Fortran, which of course is an abbreviation formula translation, right? So this is for scientists. But what if you're not a scientist? What if you're a business person? Well, then Grace Hopper does essentially this for us with a common business-oriented language. And notice that in a sense, business people and scientists have this in common, which is they don't really care about the details of the machine. They want to be able to express their ideas with all those details hidden from them, and they would like to be able to have their code not tied to a particular hardware. So having a high-level language makes sense there, whereas having a high-level language doesn't seem to make sense for people writing system software. Who can tell me what this is? This one's a little harder. It is the user panel for UNIVAC 1. It's not the whole thing, of course, right? Back then, we couldn't take get a whole computer in one picture, right? But the UNIVAC 1, which I think was out in 1951, was released for business and government, is the way they said it. So this is a business machine, right? So what is it going to do? Of course, it's going to run COBOL programs, but it's also going to be focused on text processing as opposed to floating point operations. And what we'll see is that it has, part of its instruction set is binary coded decimal. Anybody here doesn't know what binary coded decimal is? All you guys old enough to know what binary coded decimal is? We have with great disdain because it's so wasteful of what the computer can do, but it's a nice way to think about it if you're a human being that's used to, happens to have 10 fingers. On the other hand, this machine doesn't do BCD. This is called a LinkAid, and it was sold to laboratories. So this machine does do floating point processing. It doesn't have BCD. It's not designed for text processing applications, but it's designed to be able to handle Fortran. And that's kind of the state of the art in the 50s and early 60s, that we are talking about kind of two different families of both hardware and software. You're either doing scientific kinds of things or you're doing business kinds of things. But then in the 1960s, IBM, already the leading manufacturer of computing hardware at the time, released a product that firmly established themselves as dominant in the industry. It was an incredibly successful product, and it was called the IBM System 360. Those of you in the front row might notice this big red dot there. Do you know what the big red dot is? Does anybody know? It's the big stop button, right? Science fiction writers were writing about the Forbin project and all these things where the computer goes completely crazy. And so we had to have a big red button that you could just stop the machine by slamming, right? We don't worry about these things now. We have AI, so we get to worry about AI instead. But I used to work at Boeing, and as a Boeing employee, I know what the 707 in the Boeing 707 stands for. The first jumbo jet was the 707. Do you know what the 707 stands for? Nobody knows. I know. I worked at Boeing. I can tell you. It stands for absolutely nothing. Some marketing guy said, oh, 707, it sounds kind of sexy. It's a James Bond kind of thing. That's a great, well, let's do that. It just suggests jumbo jet, doesn't it? So when I saw the System 360, I thought, well, it's just a number, right? It's like the Model 1 or it's the 707. But it turns out, no, 360 actually means something. Does anybody know what 360 means? Why is it called the 360? What does that mean? What?
To go all around, full circle.
360 degrees. Why did they want to say that? It was because it's round? No, it wasn't round. It has corners, like a decent computer would. Why was it 360? It's because now one new computer fills all your data processing needs, right? It's country and Western. It does both science and business, right? So how do you design a machine for both science and business? Well, it's pretty simple. You take all the instructions that you expect in a business machine and all the instructions you expect in a scientific machine, and you just put them all there. So it featured, binary, decimal, and hexadecimal floating point calculations. The instruction set was so huge that it was the first instruction set that was actually implemented in microcode, because the instruction set itself wasn't going to be done in hardware. Instead, they invented a new coding for that. It also did something interesting. It wasn't the first machine to do this, but it did 8-bit byte addressing. Now, we're so used to that today, we don't even think about that. If you teach young people today about computers, you'll say, well, a computer has a bunch of bytes in it. And what are bytes? Well, it's these things with 8 bits in them. And that's just how computers are designed, right? But we had to figure that out. Originally, computers some of the early computers had, the smallest addressable item was a 36-bit word. And why 36 bits? Well, you can put 7 ASCII characters and have a bit left over. And why would you do that? Why have your addressability only down to the nearest 36 bits? Why would you do that?
Less wires.
That's right. You have fewer address lines, right? And if hardware is your expense, forget those programmers. Those are cheap. The computer is expensive. So if hardware is your expense, then you'll do those kinds of things. And those kinds of experiments needed to happen. We needed to kind of figure out what is the best thing. And the 360's success, with the 360, they said, look, if we're going to do text processing, we need to be able to address individual characters. And so that's where they had the 8-byte addressing. In fact, it essentially established what we would call the C machine architecture about a decade before there was C. Speaking of the decade of C, we're now into the 1970s, and who can tell me what this is? This is Bell Labs in New Jersey. And Bell Labs had 3 important things that led to the invention of Unix. One was they had a bunch of smart guys like Ken Thompson on the payroll. They had something else. They had a requirement. Bell Labs filed a lot of patents. So Bell Labs had its own patent office. And when it filed patents, they had to be nicely prepared. And so they were paying a lot of people to typeset patent applications. And they also had a kind of unused PDP-8 that just happened to be sitting there. And Ken Thompson, who would like to play with a PDP-8, said, if you'll give me the PDP-8 to play with, I'll write you a typesetting system. And so for those of you who've ever played with NROF or TROF, those are the reasons that Unix exists. It was to create typesetting applications, and that's what AT&T was willing to allow him to have resources and time to make a typesetting system. So Unix became very popular, has been very successful. And what was Unix written in? What's Unix written in?
C.
C. That is absolutely wrong. Unix was, of course, written by system software people. And what do system software people write? Assembler. So Unix was written in assembler on the PDP-8. When we got to, well, I shouldn't say we, when it got to version 4, they decided, well, we need to make this portable. Well, it's written in assembly language for PDP-8. Writing it for any other machine is going to require a rewrite. But if you write it in assembly language, you're going to rewrite it with every port. So Unix was rewritten in portable assembler. It was written in Dennis Ritchie's C language. It turned out that C was very, very popular. This is a little bit of a surprise to some people because they say, well, this is system programmers. They don't want to write a high-level language. They want to write in assembly language for the reasons that we talked about. But it turns out, no. Systems programmers are just like everybody else. Hide the details from the machine that I don't need, and don't tie me to a particular machine architecture. Of course, system programmers do have one requirement that's different from scientists and businessmen in that sometimes they do have to access the machine at very low level. And C was designed in a way that would allow us to do that. So C became very popular and is still used today in a lot of systems programming architecture. C has a kind of a drawback. This is my personal opinion, but at some point, maybe at about 50,000 lines of code, C becomes not an ideal language to work on a particular project, because C, written to be a portable assembler, doesn't support high-level abstractions. And if you're writing a really large code base, that's what we would like to do. We'd like to have high-level abstractions so that we are not distracted from the ideas by a lot of details. So now we're going to go into the 1980s, but now that we're in the 1980s, I'm going to take you back in time, and and we're going to talk about these two guys. If I stand in front of the names, can you tell me who they are? Dahl and Nygaard, they actually won a Turing Award for object-oriented programming and their work on Simula 1 and Simula 67. So Kirsten Nygaard here was a professor at a university town in Denmark, where, what's that? Oslo. Yes. And who are we going to talk about that went to school there?
I know, I'm from Oslo.
Yes. Oh, I wasn't thinking of you. I was thinking of Bjørn Stroustrup, but I'm sure they're proud of you as well, right? So Bjørn studied under Kirsten Nygaard, and Kirsten, of course, taught him all about object-oriented programming and Simula. And Bjørn graduated and was accepted at Churchill College in Cambridge and was working on his PhD. And as part of his PhD, he created a simulation to get data for his dissertation. And when he ran it on the university computer, the administrators pulled the plug because the program bogged down the computer. And so what happened next, I'm going to break an important rule of presentations. I'm actually going to read you a couple of slides of text. But I'm doing this because it's a quotation from Bjørn, and I think it's so important. And it laid the foundation of what C++ is all about. So what he said was, so I rewrote my simulator from Simula into BCPL, and all of the high-level structure disappeared. I should say BCPL was a predecessor to C. So it was a kind of a portable assembler. And all the high-level structure disappeared. All of the nice organization that had helped me debug and helped me design disappeared. But the resulting BCPL, once I had debugged it and lost half my hair in the process, ran really fast. It could use all of the resources of the machine. It could communicate with anything on the machine. And I got my data, and I got my PhD. I came away with the opinion that I would never again want to attack a problem with tools that were fundamentally unsuitable. And in particular, I don't want to make the choice between elegant, which Simula was for this problem, and efficient, which BCPL was. I want both. And that has been sort of one of my guiding lights. If you give people the choice of writing good code or fast code, there's something wrong. Good code should be fast. And this is the foundation of C++ programming, which is that I want my high-level abstractions, but I don't want you to charge me for them. That's what we're trying to do here. So Bjørn gets his PhD. He goes and gets a job at Bell Labs, where they write in C, and so he starts working in C, but he wants to be able to write simulations. He's thinking like an object-oriented programmer when he tries to do simulations. And so he starts working on a project called C with classes, which is based on C, but it extends the language in a way that starts to support some high-level abstractions. And one of the questions that has been posed to Bjørn, probably many, many times, but I think it's kind of instructional to talk about not just how Bjørn thinks about the problem, but how C++ programmers tend to think about problems. And the question was, do you ever regret that you based C++ on C? Because C comes with a lot of baggage. Those of you that were in the lightning talk yesterday where we talked about Eastcons knows that declarations in C are not necessarily pretty things. And of course, C++ has inherited all that. And so there's a lot of baggage that came with the decision to base C++ on top of C. And so that was the question. Do you regret having made that decision? And Bjørn says, no. Bjørn's famous for having said, you know, you don't look back, no regrets, you move forward. But he says, this isn't a regret at all, because if I hadn't based it on C, I would have based it on some other successful language. Because from his point of view, notice there's lots and lots of languages that have been created, literally thousands of languages. Many have no more than a handful of users ever. For a language to be successful, it's kind of a rare thing. It has to have a lot of stuff going for it. And maybe the most important thing that a language has to have going for it to be successful is not what its strength is, but what its weaknesses aren't, if you'll understand that. But so what he's saying is that C was already a proven success. And rather than reject that and say, we want something that's pure and doesn't have any baggage coming with it, we're going to base on something that's proven to be successful. And so there's so many ways that a language could go wrong. We base it on C. We know what capabilities it has, and then we add support for high-level abstractions there. So during the 1980s, after it was renamed C with classes to C++, the usage, the number of users for C++ doubled about every 7.5 months. Which is fairly remarkable given that although a number of companies have championed languages, we can look at, say, what Apple has done at Swift or what Sun did with Java, and they promote the language for reasons of promoting their platform. But AT&T looked at C++ as a tool for internal use. They spent no money at all trying to promote the use of C++, but it caught on. And as I said, the number of users doubling every 7 months, 7.5 months in the 1980s, it became quite successful. So this is now, we're finally at the first chapter of the book, and we're going to ask the question, why does anybody choose C++? It's a choice of an awful lot of software developers. Why is that? Well, again, it's this high-level abstractions at low cost, but we're not leaving out low-level access when you need it. Most of the time, I want to be hidden. I want to have the details of the machine hidden from me, but if I need that, I want that access when it's available. Wide range of applicability. We see C++ used in an awful lot of industries where what the industries have in common is essentially nothing but the fact that they use C++. We want, of course, again, highly portable, and in some ways a better resource management option than other languages. So I'm not going to go through all the different high-level abstractions that we support, except to say that the theory on these is that we want to have these high-level abstractions that allow us to build larger and larger code bases, handling more and more complicated problems without getting distracted with details. And we do this without paying the additional cost for it. So I will talk about user-defined types because that is so crucial to C++. In C++, that's how we solve a problem. How do you solve a problem? You create a new type. Right? That's what we do. And so it's very, very important that user-defined types have the power and expressiveness of built-in types. You can do almost anything with a user-defined type that you can do with a built-in type. There's still a few limitations, perhaps, but not many. If you can do it with a fundamental type, you can probably do it with a user-defined type. And the power of what you can do with a user-defined type is great with very, very low overhead. So, for example, in the standard library, we have complex numbers. Complex numbers are very important for certain domains, and there isn't a push to make complex numbers fundamental types. We have a library. If we made them fundamental types, well, they'd be built right in. How convenient. They wouldn't be any faster, because we can't make them faster than what the library can already do. And because of our operator overloads and things like that we can do, we can manipulate those user-defined types, those complex numbers, just as if they were built-in fundamental types. We also have, for example, user-defined pointers. We have, one example is a unique pointer. Unique pointer has literally no overhead of a native pointer. What you can do with a unique pointer is much safer to use, and yet, because all of that is inlined, there is no additional overhead. You write code without a unique pointer and compare it to the output. With a unique pointer, it's exactly the same, and yet the unique pointer is much safer to use. Function pointers, again, in fact, a function object, because of its ability to inline in certain cases with templates, might actually be more performant than actually a real function pointer. So these are the kinds of things that you can do with user-defined types, a lot of power, and yet no overhead. Also, there is no particular programming paradigm that's forced on the user. There's a number of different paradigms that are supported as first-class citizens, and you can mix any of them. Nothing is forced on you. I think of C++ as a language for building libraries. That's what it is from my point of view. That's what it's all about, is I can build libraries so that users have the ability to have powerful libraries that are efficient and can be used safely, have natural syntax, and high-quality automatic resource management. I don't, as a user of a library, have to be responsible for saying, oh, I'm finished with this, now free this resource up. That's done for me automatically by the library. There's some burden on the library author, but as a user, C++ libraries can have all of these features and be very easy for me to use. And of course, always keeping in mind the zero overhead principle. And I want to make clear what the zero overhead principle means. There's two important factors. One is, if you don't use the feature, you don't pay anything at all. The reason this is very important is because we want to be able to use C++ in in environments that are, have very low resources, very small memory footprint, perhaps very tight windows. And if C++ required a large and expensive runtime, that wouldn't be appropriate for that sort of thing. The other thing is, when you do use it, you pay no more than if you coded it by hand. So zero overhead doesn't mean there's no cost to the feature at all. What it means is that the feature doesn't cost you any more to use it through the language than if you were to write it yourself. So when I first started using C++, it was looked on as the least efficient option, because everybody was looking at C, and so you know, if you use C++ and you call one of them their virtual functions, well, there's extra overhead going on there, and that's really expensive. Now, of course, we think of it the exact opposite. We say, well, C++ if you really need performance, but otherwise use a different language. But the point is that that additional overhead with the virtual function, you can do function dispatch much less expensively, but not if you need the features of what inheritance gives you. You're not paying any extra because you're using this language feature. It is a systems programming language. It has low-level hardware control. You can use it to do system software, and the reason is because all of this comes free because it's a superset of C. It was a proven language to do all of this that was used as the basis for C++. So making that decision, you get all these features free. The payoff is you also get all of the baggage from C, but it was a trade-off that Bjarne was willing to make. I'm going to talk a little bit about management of user-defined types because I think it's an interesting contrast. If you have an object-oriented programming language, there has to be a way to ask for an object, and the language is going to allocate some memory on the heap and then prepare that memory to be an object, something which in C++ we would call a constructor. And in object-oriented languages, that's what they do. In C++, of course, do that as well. But in C++, you might not just want to put it on the heap, you might want to put it in static memory. If we have an object that is going to be the lifetime of the application, why spend the resources to allocate the memory? Just use static memory. In addition, we can also put it on the stack. Now, stack-based memory is much less flexible to use. We can't control the lifetime of stack-based memory. Well, we have a particular lifetime model that's forced on us. But the fact that it's so inexpensive to allocate means that for a number of situations, allocating objects on the stack is a big win for us. And a number of object-oriented languages don't give you that option. There's no way to do that. But C++, that wouldn't be good enough. In C++, it's actually possible to initialize an object in any arbitrary place, which is what vector, of course, does. You have an arbitrary buffer of memory, and the lifetime of objects is controlled by the library and not limited at all by the language. That's the kind of thing that a C++ kind of language is going to demand. There's also low-level access. Again, we talked about it as portable assembler, but there's things that we as C++ programmers are concerned about that other language programmers aren't concerned about, not because they've solved the problem, but because there's nothing they can do about it. They don't have control over low-level layouts of how objects are laid out in memory. That's determined entirely by the language with no control. Now, we don't have to worry about how things are laid out if we don't care, but if we're worried about things, then we can specify how objects will be laid out in memory. What Bjarne has always said is, don't solve the specific problem, solve the general one, which is one of the reasons why C++ is designed to scale, both scaling down in situations where you don't have many resources. C++ is still a valuable choice to scale down, and also to scale up. Both when the application itself has to scale up, there's lots of data, maybe lots of cores, lots of resources thrown at the problem, but also when those resources may in fact be engineers, the number of people working on it, the fact that the language itself supports separate module compilation and the ability to create libraries that can work with very low coupling allows the project itself to scale as well as the application scaling. And of course, high portability, not a surprise given that it's based on portable assembler, but the fact that it's based on what we call the C machine model, which has minimal hardware requirements and pretty much universally supported by hardware, means that there are C++ tool chains on almost all platforms, and it is in fact the only high-level language alternative that's available on all the mobile platforms. and we can write software in C++ and port these to all these different programs, all these different platforms. So the other thing that makes that's an important part of the C++ story, I've been comparing C++ with C as a systems programming language. But C++ has the advantage there that it supports high-level abstractions. And I've been comparing C to other languages that support high-level abstractions, talking about the advantage that it has in systems programming. But there are other languages out there that have that same combination. Most of them are more recent languages like Rust or Go, where they're trying to be systems programming languages but support higher-level abstractions at the same time. But what distinguishes C++ from that is the level of industry support. So if I were to offer you this wonderful new language I invented, the syntax is to die for. It's like butter melting in your mouth. You're going to love this syntax, right? And what you can do with it, it has really cool abstractions, and it's really a powerful language. And you're all excited and say, well, I can't wait. We're going to use this on the next project. It's like, well, we'll have to, you can't hire anybody who knows this language yet. Oh, that's fine. We'll bring them in and we'll train them. It's like, well, you can't hire anybody who can train on this language yet. Well, that's fine, we'll buy them books. Well, you know, the point is that C++ has huge industry buy-in. Now, the downside to that is it also has huge baggage. But that baggage comes with the fact that it is possible to find literally millions of people on this planet who understand C++, and lots of books, lots and lots of videos, lots of industry buy-in, lots and lots of libraries. And that's what distinguishes it from other languages that have the advantage, because they're more recent languages, to have learned from the mistakes of C++. They have less of the baggage that C++ has, but the trade-off is they also have less industry investment. All right, one example I want to talk about is garbage collection. I don't know if in this lighting you can see this, but I have a certain amount of gray hair. And every one of these gray hairs is a memory leak. It's amazing I remember anything. So I have a great deal of sympathy for why we want to have garbage collection. I have fought the memory leak wars, the double disposes. I understand that. And garbage collection is, in fact, a valuable solution that's used an awful lot. But like any engineering solution, there are trade-offs. There's advantages to garbage collection, and there are disadvantages. And among the disadvantages, we see that you may in fact find that memory is not released at all. It may be the specific time it's released is not under your control, if it's ever released. And when it does in fact get released, it may in fact have the effect of freezing your computer because you have no control over this. And in fact, in some application systems, the amount of unused memory has to be large in order to make the garbage collection work. So this is a solution to this, but it's not really the one that we want for C++. One of the reasons is that we really want to generalize the solution. Memory is not our only resource. And so garbage collection is great for collecting memory, but what if among our resources are file handles or network sockets or some other operating system scarce resources that we want to handle and not leak? So with C++, we use this feature of deterministic destruction to create something called an RAI object. Some people say that's resource acquisition as initialization. I prefer to think of it as responsibility acquisition as initialization. Every responsibility that has to be discharged is put into an object with the appropriate lifetime, usually on the stack, perhaps in an object, and then it discharges when that object goes out of scope. Other languages may, in fact, have the finally keyword, but I think finally violates DRY. What's DRY? Yes? I had him going. I think Guy was going to go 6 or 7 times, right? Right. The finally keyword is essentially saying you use this type as the user, you need to clean it up. That's not the C++ model. The C++ model is I'm going to use the type in your library, the library needs to clean it up. That responsibility has to go to you. If I, as a user, have to clean it up every time I use it, that doesn't sound like very much fun, for one thing, but it's also kind of a maintenance nightmare. And so that's not the C++ way. Have you ever noticed that Michael Case's name doesn't come up in enough talks? All right, so we're now at the 1990s. And After growing during the 1980s at the rate I said, a very high doubling rate, we get to the 1990s, and we're now entering this time when object-oriented programming is the craze. This is what everybody's talking about in the 90s. You might notice from my tone of voice that I don't think object-oriented programming solves all our problems. It might have been a little bit overhyped. But I will say this, that object-oriented programming does map pretty well to GUI programming. And of course, in the 1990s, GUI programming was a big deal. This is when the Windows Mac wars and the object-oriented programming wars were coming together. And so there was an awful lot of interest in object-oriented programming. At that time, C++ was pretty much seen as the object-oriented language. And so a number of large companies that had made significant investments in C++ approached Bjarne Stroustrup and said, we need to standardize this language. It needs to not be under the control of one guy. It needs to be an international standard. And so that's what they started working on. Now I want to introduce Alex Stepanov. When everybody else was excited about object-oriented programming, Alex not so much. He was working on a different paradigm, and he coined the term generic programming. And he was working on a library that worked on, focused on algorithms. And the idea was, I'm going to implement an algorithm once and not ever have to implement it again. We'll implement it in such a way that it's highly reusable. It's generic. The fellow on your right, that's Andrew Koenig. Andrew was the chair of the library subcommittee of the Standards Committee during the 90s, part of the 90s. And so he reached out to Alex and said, they both worked at Bell Labs, so he said, are you going to submit your library? Because he knew about the library. And Alex said, oh no. He said, this library, well, first he said, you know, the committee is very close to releasing a standard. Little did he know. And he said, this library is much larger than anything the Standards Committee has considered before. My library is, you know, a considerable investment of time for them to try to standardize it. Furthermore, and this is a little bit hard for us to understand today, particularly for those of you that were introduced to C++, where the generic algorithm library was part of C++. But I was programming in C++ before this was part of the standard, and I can tell you that the first time I looked at this, I said, what? Because at that time, all containers were object-oriented. Remember, this was the decade of object-oriented programming. And so when you put an object in a container, what that meant was you copied the pointer to that object into the container. Why? Everything's object-oriented. Of course, it's a pointer to a base class. I don't even know what the object really is. I just know it's a container of shape pointers or whatever it is, right? And so the first time I studied and looked at this library and I put something in a vector, I said, what do you mean? I haven't put it in, it's still right here. I put a copy of it in the vector. I didn't put it in the vector. It was a completely different way about looking at the world. And Alex was used to this. He would explain this library to people, and they would not get it. And so he said, the library, the Standards Committee is not going to get it. So I'm not going to propose it. And Andrew said, well, I think you're absolutely right. The Standards Committee is not going to accept your library if you don't propose it. So Alex recognized that he was being told he needed to propose it. So he and his team went without sleep for several weeks as they made a formal proposal. Alex went to the Standards Committee and made a presentation. And I will give the committee a lot of credit, because even though initially he was absolutely right. Initially, the committee said, this is this huge thing. It's unlike anything else. You know, the mandate of the Standards Committee is to standardize existing practice. This was not existing practice. There were not very many users of this library from some research guy at Bell Labs, right? So, so the first initial response of the committee was no. But as they thought more about it and recognized it, and the penny dropped, they got it in ways that I'm afraid it took me longer to get when I first looked at it. But the committee, to give them credit, they did recognize it, and they realized they couldn't release a standard that didn't have this as part of the standard. So of course it became the C++ standard template library became part of the standard. So what do we have? What we have is incredible growth during the 80s, compounded in the 90s by becoming an international standard. So we've got a lot of momentum here. But when the standard ships, Beeman Dawes, who took over from Andrew Koenig as chairman of the library committee, he recognized a problem. The problem is that if the library committee is responsible, or the subcommittee, is responsible for standardizing existing practice, that means we need to have widespread use of libraries. Well, there were widespread use of libraries at the time, but they were all proprietary. There was no widespread use of any library that could be standardized. There just wasn't. So what Beeman said was, what we need to do is, and he got together with other people in the standard library, including Dave Abrahams, and they created Boost. Now, again, young people today, I know I sound like, get off my lawn. Young people today don't appreciate, because you go on GitHub, you want to give away a library. At the time Boost started in 1998, that was a very radical idea. The idea that you could just go to a website and download a library and go. That was pretty radical at the time. But that was their vision, was not just a place where libraries would be free, but you couldn't just, I'm working on this project, I did this little library, you can have it. No, these were peer-reviewed libraries, very high bar to establish these libraries. So we have high-quality libraries available for free. We have an international standard, which has the STL in it, a very, very innovative and powerful way, a new paradigm for how to do programming. So the momentum at the end of the 90s for C++ was very, very high. And then we get to the 2000s. And we have this. So with the momentum going great, we run into this, and it turns out that we have Java, which supports object-oriented programming, which, as I said, that was going to solve all our problems, right? Here's Java. It's the language of the web. What does that even mean? I don't know. Oh, it means that, okay, it's the language of the future. So let's get on board with Java. It's almost as fast. Well, in the 2000s, that was good enough. We'll talk more about that. And it was easier to learn and teach. Imagine, you can kind of imagine some college professor calls up the head of the computer science department. He says, hey, the class where we're teaching C++, he says, yeah. He says, if we switched to Java, we could skip chapter 9 and wouldn't have to talk about pointers at all. So that's kind of what we got. Now remember, this is the 2000s. Desktop computers were so powerful that operating system vendors were deliberately adding gratuitous animation to justify you buying new hardware, right? We'd solved the performance problem. Computers were now so fast that you didn't need to buy a new computer because it just didn't need to be faster. And in that environment, why would you use a language that's harder to use even if it gives you better performance? Particularly, maybe it only gives you 10% better performance. And it's a lot harder to use. It has all this, it comes with this baggage. It has these templates. Oh my gosh, templates. Generic programming, who understands that? It has operator overloads. You write plus and it goes out and calls some function? That's crazy. And then pointers. Don't even get me started on pointers, right? So if you use a managed language, it would be fast enough. And so we have these virtual machines, the Java virtual machine, the Microsoft virtual machine, and they were easier to use than C++, and a lot of colleges switched over, right? Why teach stuff hard when you can teach stuff easy? And then, as I said, in 1998, the Standards Committee shipped a standard. That's great. You guys are software engineers. What do you do when you ship a version of your software? What do you do? Go to the beach? You start working on the next version, right? Sure. But the Standards Committee had a problem. Because in 1998, this was not controversial. Everyone knew that it's going to be 4 or 5 years before there would be an implementation that would completely support the standard. It's very different than today. Again, I know, kids today you don't appreciate, right? But when C++ 11 comes out, and in 2012, there are 2 versions that are pretty much complete implementations. Or C++ 14 comes out, and that year we have implementations. That's exciting. That's so different from what the committee had then. So what do we have? We have people working on the standard ships, and now they realize we want to wait for feedback on this before we start adding more features. Well, now that doesn't sound nearly as interesting. And so what happens to the committee? The committee shrinks, right? Why? We're not going to do anything interesting. And when we do start standardizing things, it's going to be a few years before it's in users' hands anyway. It just doesn't seem like a very interesting kind of thing to do. So 2000 turns out to be a bad decade for C++. It looks like it might become the new COBOL, right? Legacy apps only. But that's not what happens. Instead, the beast roars back. So what happens? Well, it turns out that desktop computers aren't the only computers. In fact, you know, from a numbers point of view, desktop computers aren't computers at all anymore. What are computers now? Well, computers are this thing, right? This is a computer now. And it turns out that even though this runs pretty fast, I still care about performance. Why? Because it's got a battery in it, right? So even if it's as fast as possible, I still want that code to be efficient. Now, this doesn't have a battery in it. At least I assume it doesn't. But I still care about performance. Why? Because I'm thinking about it in terms of performance per dollar of hardware, or performance per watt of power, or performance per watt of cooling. Right? Performance is still important. It turns out that the 2000s was kind of an anomaly. We had computers that were more powerful than the jobs we needed them to do. But that's not the end of the story. That was just one little tiny spot in the history of computing. Computing moves on. It moves to different kinds of things. It moves into the cloud. It moves into your pocket. Right? So James Hamilton of Amazon did this analysis of what he called modern high-scale data centers. And I want to explain what he means by that. It may seem like it's self-evident, but what he means by modern high-scale data centers is he's talking about data centers where essentially all of the computers are running the same software. It's not a whole bunch of different kinds of jobs. What he's talking about is something like Google or Facebook, where you have thousands and thousands of machines running the same software, part of the same application. And in that situation, he listed the costs in terms of decreasing costs. So the highest cost, of course, was the hardware to buy the servers. And next was power distribution and cooling. Notice it costs more to cool them down than it does to power them. Interesting. And then, of course, there's more hardware, the networking equipment, and then there's other infrastructure. So a couple of things to notice here is the top three are directly related to software performance. If you can make the code 10% faster, you can reduce the cost of the data center by 9%. Almost 100% hits the bottom line, right? That's how important performance is. The other thing is, where are the programmers and IT professionals? Where are they? Well, the cost of writing the software is insignificant compared to the cost of running it. These are the asterisks. So if you're writing in a language that optimizes for programmer performance, programmer proficiency, maybe you're optimizing for the wrong thing. All right? So the other thing is, of course, the big thing that happened in the 2010s is in 2011 was a new standard that came out. Feels like a new language. And in fact, it did feel like a new language in a lot of ways. It practically was a new language. If you look at the page count, almost doubled. But something interesting is, one of the biggest complaints about C++, and I've never refuted this, is it's just so complicated, right? Is there anybody who ever said, well, you know, C++, it's not intellectually challenging enough to understand the language, right? But the problem is, how do you simplify something? Well, the best way to simplify something is to remove all the complication. But we can't do that because we're going to break backward compatibility. And given that there's, I have no idea, trillions of pounds worth of value in the C++ software, breaking that software is a huge problem. We can't do that. But it turns out that the Standards Committee has found a number of ways to simplify the language by adding to it. And at first that sounds like, well, how could you do that? But it turns out, no. There's a number of features that main job of those features is to simplify the language. And uniform initialization is almost in that category. There were a number of things added to the language that were specifically to make it a modern language. Things that we would expect in a modern language, like lambdas, lambda expressions, maybe Unicode support, and then some things like tuples and smart pointers, things that we would expect in a modern language. And then there were maybe some things specifically for library authors, and some people don't appreciate those features as much because they say, well, I'm never going to use that. Well, yes, you are. Somebody else is going to do the hard work, and you're going to benefit from that by using those libraries. And then there were some other areas, brand new areas like multi-threading. Whoever thought about that? But also move semantics, something that other languages don't have enough control over what's going on at the low level to even think about something like move semantics. Something else that happened didn't actually happen in the 2010s. It actually started in the 2000s, but it wasn't really interesting to C++ programmers in the 2000s, and that is LLVM, clang. Clang existed in the 2000s, and it was really good for C, but it wasn't really up to doing C++ yet. And that clang as a C++ compiler happened in about 2010, 2011, that kind of time frame. It began to be able to do C++. And of course, having a new compiler means more competition. The big areas for clang are error messages and build performance. If you take a look at a compiler that's not clang from that era, say 2010, and look at the error messages from another compiler in that and compare them with today on that compiler and see how much they've improved, you realize the impact that clang has had. But I don't think the biggest impact that clang has had is strictly on competition. I think that the biggest impact clang has had has been that it's not designed to be a compiler. It's a toolkit. We make sanitizers and other tools that are even used by other compilers because, of course, it's open source, and so other compilers can benefit from the work that's done in clang. Also, as a test bed for language features. Of course, libraries can easily be tested on any compiler, and I can give you my library. But if I have a language feature I want to test, how do I do that? Well, I have to have a compiler that I can make changes to, and that's not always easy. But clang now has an opportunity to do that. Something else that's come into its own, of course, is open source. When I talked about in 1998, it was a different world with open source. But open source is more and more what we expect, and it's more and more common. And open source means that we're not linking to a library. Instead, we have the source. And the compiler can do such a great job with source when we have the source rather than a library to link to, particularly when the source is templates. So open source really plays to C++ strengths. C++ is not necessarily the kind of thing we would expect to see in open source libraries, but we look again and find out that the rank of C++ in open source in GitHub actually goes up in this time frame from 2010 to 2011. Remember, we talked about the standards committee when it shipped in 1998. What happened to the committee then? It shrank. But in 2011, the same thing didn't happen. Why is that? Well, I gave you part of the answer. It's because now tools were tracking the standard much more closely. So that not only was the standard implemented mostly in 2012, a year later, but many, many features had already been implemented. So we still see this today, where we go to the standards committee, something new is in the language, and after we come home from the standards committee, Richard Smith puts it in clang, and then there's a new feature in the language that users are using long before it actually, the standard itself actually ships. This is a new world, so different. But what happened was that the thinking about C++ as a language changed so much. People used to think of it kind of like Latin, right? It's there and it's useful for some scientific purpose or something, but it doesn't change. And then when 2011 shipped, suddenly, like, oh, C++ can change? And so there was a great deal of interest in the committee. So instead of shrinking, what happened was the committee got a lot larger and created a number of different study groups. What's our new study group number now? Latest study group is 16, so there's 2 that aren't even on here, right? The point is we're now parallelizing the work in the standards committee, but the reason is, it's not just that it's better organization, it's that there's so many more people involved because they're thinking about standardization in a different way. It used to be standardization was this process that once you got something into the standard, it would be another 4 years before the standard ships, and then it's another 4 or 5 years before the tools ship. Now it's different. You get something in the standard, users are using it possibly within a year. That is inspiring, and that causes people to want to work on the standards committee. And that creates a lot more interest in what C++ is. Something else happened in 2010, and that was the formation of something called the C++ Standard Foundation. This is an organization that's job is to promote C++. And as I said, AT&T had never done that. There's no organization whose job it was to promote C++. So they don't run commercials, but they do have a website that you can go for news status discussions about C++. And in fact, they've now taken over. Bjarne used to have a Q&A on his website, and there was also a FAQ, and those have been combined into what's called the Super FAQ, and you'll find that on this website that's been combined. Another tool, kind of demonstration of a great interest in C++ was a new IDE. I'm not doing this to plug C-Lion. The reason I'm talking about this is because I'm going to share with you some of the work that Anastasia did before C-Lion came out, where JetBrains, Anastasia, who's in the next room over there, did this research. I asked her for permission to share it with you, and what she said was, we'll be absolutely certain you tell people where the sources came from. And the reason she's saying that is because this may be the best information on C++ available, but best doesn't mean good. This information is really hard to find, and so this is a guess, perhaps, right? It's an attempt. But the belief at the time was that there was about 4.5 million C++ developers. And that was a bit of a surprise to me, because up until then, most of the numbers that I'd heard were on the order of 3 million. So this was more people than I had expected. Kind of showing how the popularity rank is, putting C++ as pretty high, certainly for systems programming languages. This was the bigger surprise to me as a North American. Of course, I'm thinking I'm the center of the universe. It turns out, well, you know, there's 3 times as many programmers in Europe and Asia as there are in North America. I think I need to be going to more conferences in Europe, right? And then almost half as many people in South America as there are in North America. This is a huge surprise to me. Thought that was very interesting. Also interesting was the success of C++, again, in Europe and Asian countries. More recently, I've had a conversation with someone who is involved in the C++ community and regularly receives resumes from college-level individuals about C++. And one of the things he told me, he said, you know, I'm really kind of surprised by this, but we're getting consistently really high applications from Poland and Russia. Whatever they're doing over there to teach these, you know, 1 or 2 really good applications, that means it's a particularly individual who's very bright. But when it's consistent, it means it's the educational system that's very successful. So I find that very good. And when I think about college education in the United States, I kind of shake my head, right? The industry distribution, I kind of suspect there's not 3 or 4 times as many people in finance as anywhere else. I think, you know, this came from job ads, and I think the people in finance just run more ads than anybody else. But it does give you a little bit of idea about the distribution of industries that C++ programmers are in. CPP cast, how many of you have listened to at least one CPP cast? Oh, that's terrific. I assume the rest of you don't have commutes? Is that the deal, right? So CPP cast is now very close to its 3rd anniversary now. I think they're on episode 145 or something like that. Absolutely wonderful podcast if you're at all interested. Their format is to interview people who are doing something interesting in C++. There's a new video podcast that's going to go audio. Those of you that want stickers, come and talk to me. There are also places on the net where you'll find interesting places to get C++ support. Stack Overflow has tens of thousands of questions. It's very, very active for C++. cprogramming.com. I don't actually have Slack on here, but there's a CPP Lang Slack. If you're not on that, you're missing out on real opportunity to stay up to the minute and ask really smart people who are online all the time interesting questions. CPP Reference. Notice CPP Reference is actually up to date for C++ 20. Because this is a wiki and gets lots of good community support, this is an incredibly valuable reference. Those of you who haven't used CPP reference are really missing out. You need to look into that. It's very valuable. Not only does it have information about all these standards, anytime you look at something, it will tell you what version of the standard it was introduced or what version it was deprecated or what version it was changed. Very valuable reference. And of course, Reddit, which was only started, the CPP subreddit was only started in 2008, and it took 4 years to get its first 10,000 subscribers and enter into the top 1,000 subreddits, but it has gained about 10,000 new subscribers about every year. So it's very, very popular venue for information about C++. There's a number of different user groups. If you go to, again, the isocpp.org, we try to stay up to date with user group by country. There's also a map. If you zoom in, you get the actual, the way this map works is, as you zoom out, it coalesces. It says there's 50-some user groups in Europe. And and so this map gets updated about twice a year or something like that. But it does give us a picture of the number of, most of these user groups were not in existence in the 2000s. So these user groups are in the last, most of them, 5 years. A number of different conferences. These are some of the major conferences that have started since 2010, or in this case, switched from being about Boost to being about C++. But the number of conferences is getting so much so fast that it's hard for me to keep up with them all. In fact, it's because it's hard for me to keep up with them all that I created a wiki page to keep up with all the conferences and encourage you to go there. These are divided by, again, by continent. There's also, this is kind of new, so there's not a lot on it yet, but we've actually created a community events calendar that you can also find by looking at the wiki. And we're trying to put both conferences and user group meetings, and perhaps we'll put things like deadlines and things on there. We haven't. This is very much still a work in progress. All right, any questions about the state of C++ or its future? Wow, did I just exhaust you? Or here's a question, okay.
I think first is brilliant talk. Thank you very much.
Oh, thank you.